Okay, in this lecture we're going to continue learning more about acids and bases. Now, one of the things that we're going to talk about is what's called a salt. Now, everyone's familiar with table salt, which we've already talked about is sodium chloride, and that's one kind of salt, but it turns out that there are lots of other kinds of salts available. So we want to talk about what it is that makes something a salt, and what does that have to do with acids and bases. So let's look at a typical chemical reaction, one that actually can form table salt, sodium chloride, which we've already talked about. NaCl is the kind of salt that you would have in your cabinet that you would put on food to make it taste a lot better. So the reaction is we have hydrogen chloride, HCl, which is added to sodium hydroxide, NaOH, and the hydrogen chloride is an acid, which means it's donating protons. The sodium hydroxide is a base, which means it's accepting protons. And they have a chemical reaction which yields sodium chloride plus water. Now, we can imagine we've got HCl. We can think of this, the H is going to break off, you're going to have a hydrogen ion, which is positive, and you're going to have a chlorine ion, which is negative. And here you're going to break up the sodium, which we've seen before can form sodium ions that are positive, and the OH is going to form a negative hydroxide ion, which is negative. And so we can see that the NaCl is going to combine to form table salt, and the hydrogen and the hydroxide ions are going to combine to form water, and we're left with our reaction that HCl plus NaOH forms NaCl plus H2O. And if we look at that, we know that the HCl is what's donating the hydrogen ion, so the hydrogen ion comes off here, and this guy is receiving it, and so that it becomes the base and this becomes the acid. Now, the other thing that we can think about is what's formed. What's formed is water and then sodium chloride, and this is classified as what we call a salt. And so we can say that a salt is an ionic compound formed from an acid-base reaction. So HCl is an acid, NaOH is a base. We combine an acid with a base, and we end up with a salt plus water or some other product. Now, of course, sodium chloride is the most famous salt. It's the one that everyone's familiar with because of cooking, but there are other kinds of salts, and here's another very similar reaction that forms a different salt from sodium chloride. And so if I mix hydrogen chloride again, but instead of sodium hydroxide, I mix it with potassium hydroxide, I get the same kind of reaction, and I end up with potassium chloride, which is a salt, plus water. Now, here we have a table that's showing several different kinds of reactions with an acid and a base that form a salt. And so, for example, we have hydrogen cyanide, HCN, forming a compound with sodium hydroxide. You add them together, and they have a chemical reaction, and they yield sodium cyanide plus water. The sodium cyanide is a salt. And you can see there are other chemicals. I'm not going to go through every one, but there's potassium nitrate, calcium chloride, sodium fluoride. These are all salts. By the way, when I import my PowerPoint into these videos, you may have noticed sometimes the subscripts get a little bit messed up. This 3 here should be a subscript. That 2 should be a subscript. That 2 should be a subscript. This 2 should not be a subscript because it's in front, but the others should all be subscripts, just FYI. It probably will print out correctly when you print out your copy of the PowerPoint, but I just wanted to mention that. Hopefully it's not confusing. Here is another example of a salt. You can have hydrogen chloride mixing with pseudoephedrine, and you end up with pseudoephedrine hydrochloride, which is a salt. So you're mixing an acid with a base, and you end up with a salt. Now, this chemical is obviously way more complicated than most of the reactions we've looked at, but the same basic principle applies. And if you donate a proton, you are an acid. If you are accepting a proton, you're a base. And if you have a reaction where an acid and a base combine, they can form a salt. Okay, so let's do our understanding check. What salt forms from the reaction of hydrogen chloride, HCl, with potassium hydroxide, KOH? Now, we know that the H and the OH are going to combine to form water, and that leaves us with a K and a Cl. And so if I look at these compounds, the only one that fits the bit is compound A, potassium chloride. So that is going to be the compound that forms. The K, of course, stands for potassium. The Cl is chlorine. And so we know that from our naming convention, this compound will be potassium chloride. And we can see our explanation here that the potassium positive ion from the KOH is going to combine with the negative chlorine atom from the HCl and form potassium chloride. Now, we've already talked about how different chemical compounds can have different types of bonding. We've talked about covalent bonding and ionic bonding and many different kinds of bondings. And even within the same kind of bond, some chemicals are held together more strongly than others just based on their structures. So it turns out that some things that are able to, for example, donate protons, which of course would make them an acid, some chemicals, they really like to donate protons. They give them away all over the place. Whereas other types of chemicals might be more stingy. They can give away some of their protons, but they really don't like to. They don't do it as often. And so basically, this is what is related to how strong a particular acid solution will be. So as an example, we can take hydrogen chloride, which we can see in the little picture here. So this is a tank of hydrogen chloride. And by the way, under normal conditions, hydrogen chloride is a gas. So if you take a gas tank that's filled with hydrogen chloride and you have this tube that lets the gas bubble into the water and dissolve, what you find out is that hydrogen chloride just completely breaks apart and forms ions. And so you get essentially the whole shebang until that solution becomes completely saturated. And so hydrogen chloride is an extremely strong acid because if you put it into water, it will be essentially completely dissolved into the ions floating about in the water. Now, this same principle would apply if I had a base and I dissolve the basic chemical in the water. Some base chemicals are really able to accept those hydrogen ions, some not as much. And so what you'll find if I put one base in a bunch of water and another base in a bunch of water, maybe one of them would completely dissolve and the other one would only partially dissolve. And so the one that completely dissolves in the water, that's going to be a stronger basic compound. This is the idea that we're talking about here. And of course, the same principle applies when we're talking about weak acids and weak bases, but it's just the reverse. And so the example here is our little chemist in our cartoon here is pouring some acetic acid. That's basically the active ingredient in vinegar into water. Acetic acid, unlike hydrogen chloride, which is a strong acid, acetic acid is a weak acid. And so it doesn't donate protons as freely. It doesn't donate those hydrogen ions as freely. And so basically what that means is not as much of it is going to dissolve in the water. And so this would be a very much weaker solution of an acid than the hydrogen chloride. Now, it may be worth noting that this can be a little bit relative because if I have just a little bit of hydrogen chloride that I dissolve in a whole bunch of water, even though hydrogen chloride is a very strong acid, because it's so diluted, the solution I would end up with would be a weak acid. And if I take acetic acid, this guy here, and I dissolve it in water, not a lot of what I put into the water is going to dissolve, but if I put more and more in, I'm going to get a more concentrated solution of acetic acid in my water, and so that would make it stronger just by dumping more. So it is possible to have, for example, a weak solution of hydrochloric acid, which is, say, less corrosive than a strong solution of acetic acid. In other words, just by concentration. So hydrogen chloride normally makes a very strong acid, but if I just have a little bit of it, I'll have my acid be very dilute, and so it won't be as effective. Whereas if I take acetic acid, which is normally a very weak acid, but I just put lots and lots and lots in the water to dissolve, I can make a more concentrated solution, and that would make it more effective. So how can I tell if I have a weak or a strong acid or base in my solution? One way is to simply run a current through it, because in these chemical reactions, you end up with a bunch of ions, and the more of the acid or base that dissolves in the water, the more ions you're going to have in your solution. And ions are able to conduct electricity. And so if I have more ions dissolved into a solution, that solution will conduct electricity better. And so you can see this here in the figure. We have a light bulb which is connected to a battery. You can't see the battery, it's out of the picture frame. But the wire coming from the battery goes to this electrode, which is submerged in a solution, and there's another electrode submerged in the solution. So the current basically goes through the solution into the light bulb and then back to the battery. Now, if the solution is very, very conductive, when I turn the battery on, I'm going to get a lot of electricity flowing, and my light bulb will light up very brightly because a lot of current is flowing, because this guy is very conductive because it's got lots of ions dissolved in it. It's obviously a strong acid or a strong base here. This guy is a weaker acid or weaker base. How do I know that? Because the electricity, it goes through the light bulb, it goes through the solution, it doesn't conduct electricity as well. There's fewer ions dissolved in it. That means it's weaker. I can tell that because the light bulb's simply not as bright. There's less current flowing through the light bulb to light it up and make it brighter. So using electrical measurements is one way that you can determine how conductive a solution is, and that's related directly to the concentration of the ions. That will tell you whether you have a strong acid or base or a weak acid or base. Next, we want to talk about acidic, basic, and neutral solutions. Now we're going to start out talking about water. Water is nifty in that it can behave as both an acid and or a base. Not every chemical can do that, by the way. The ones that can are called amphoteric, and so I'll write that out, amphoteric. And so that's a really fancy word. Compounds that are amphoteric are simply compounds that can be either an acid or a base, depending on what they're mixed with. Now, if we go back to considering water, we know that water can donate and receive hydrogen ions. And so just water sitting together, sometimes you're going to have one of them is going to donate a hydrogen ion, and what you're going to end up with is a hydroxide ion and a hydronium ion just floating about. And of course, once you start building these up in the solution, the reverse reaction can occur, like we've talked about previously. And so you'll get an equilibrium established where even if you start out with just absolutely pure water, eventually you're going to have some ions floating about in it, and there'll be some sort of equilibrium established. Now this is always going to happen in pairs. So I've got, for example, this guy here has a hydrogen ion, which it donates over here, and that means that this guy is donating, so he's the acid. This guy is receiving, he's accepting, so he's the base. And also, it means that you have a one-to-one correspondence. So for every one of these, for every hydroxide ion, you have to have one of these, a hydronium ion. We can sum this up by noting that in pure water, for every one hydronium ion, H3O plus, that is formed, there is a hydroxide ion, OH negative, formed. Now, experiments have determined that when this happens, the concentration of each of these is very low. It's about 0.000001 moles per liter. Remember that capital M stands for molarity, which is moles per liter. And so this is the number of moles of ions you get in every liter of pure water. Now, you can see I've got the hydronium ion H3O plus and the hydroxide ion OH negative, and they're in brackets. The brackets just mean concentration of. And so the concentration of the hydronium ions is equal to the concentration of the hydroxide ions, which is equal to 0.000001 moles per liter, or 10 to the minus 7 moles per liter. Now, in a normal neutral solution, for every hydronium ion, there is also a hydroxide ion, and so they're balanced. They have the same concentration. And so the amount of positive ions is equal to the amount of negative ions. So you can imagine if they were on a seesaw, they would balance out perfectly. And that is a neutral solution. So for every positive, you have a negative, and so the overall solution is neutral. And chemists make use of something called the pH scale. It goes from 0 to 14, where 0 represents a strong acid, 14 represents a strong base, and 7 is right smack in the middle, and it represents neutral solution. So if it says neutral, that means for every positive ion, there's a negative ion, there's no excess. And specifically, we can say that in a neutral solution, the concentration of hydronium ions is equal to the concentration of hydroxide ions. So we know that water can behave as an acid or as a base. One of the things that we can do is add extra ions, and that'll knock the balance out of kilter. And so if we add hydronium ions, the H3O pluses, the solution becomes more acidic. And if we add hydroxide ions, the solution becomes more basic. So this schematic is showing some of the different scenarios that can happen. Now we've already seen that in a neutral solution, the seesaw is balanced. There's an equal number of hydronium ions compared to the hydroxide ions. But if I add a bunch of hydronium ions, the seesaw will get unbalanced. I've got more of these, and that'll drive the solution to become more acidic. And so in an acidic solution, there's a higher concentration of hydronium ions than hydroxide ions. And so this is, of course, the greater than symbol that you learned in your math classes. And so the number of these, or the concentration of these, is greater than the concentration of those. In a basic solution, you're adding a bunch of hydroxide ions and you're tipping the seesaw the other way. And so in a basic solution, the amount of hydroxide ions is bigger than the hydronium ions. So consider this question to check our understanding. Imagine we have sodium hydroxide, NaOH, and we add it to water. The hydroxide ion, OH negative concentration, what happens to it? Does it increase, decrease, or remain the same? What do you think? Well, the answer is it increases. Now, here's the explanation. The bond between the sodium and oxygen atoms is an ionic bond, and so when it dissolves in water, it separates into sodium ions and hydroxide ions, much like sodium chloride separates into sodium ions and chloride ions. So the NaOH is going to separate into the sodium and the hydroxide, and so the amount of hydroxide in the water is going to increase. Now we've talked about pH, and pH basically tells you whether something is more acidic or more basic, but really pH is a measure of the concentration of the hydronium ions, those H3O pluses. Okay, so for some of you this is going to be the scariest thing we do all semester. We've got logarithms in the house. That's right, logarithms. This is the real definition of pH. It is minus the logarithm of the concentration of hydronium ions. That's a mouthful. Let me say that again. So this log, that stands for the mathematical function of logarithm. So the pH of a solution is minus the logarithm of the concentration, remember the brackets means concentration of, hydronium ions. And so if I have a bigger concentration of hydronium ions, I'm going to end up with a bigger pH. Now, if you haven't seen logarithms for a long time and you're freaking out a little bit, there's a lot you can do with logarithms, which makes them kind of complicated, but we're going to only do one little tiny thing with logarithms, so it's not so bad. Basically, the rule for logarithms is this. If I have 10 that is raised to some number, and it could be any number, it could be -2, it could be 27, whatever number it is, and if I take the logarithm of that 10, which is raised to some power, some number, my answer is just the number. It's that easy. So if I've got the log of 10 to the 2, I take that, I end up with just 2. That's what it's equal to. Now, we can apply that to our concentration of hydronium ions. We've already seen that in pure water, the concentration is about 10 to the -7 moles per liter. And so if I take the log of that, remember it's 10 to the number, the log of 10 to the number is the number, so my pH is minus a -7. I've got a minus here, I've got a minus there, that's why I've got two minuses. What happens when you multiply a minus times a minus? You get 7. And so the pH for regular water, for pure water, is 7. So just to recap, if you have 10 raised to any power, the log of 10 raised to any power is just the number that you've raised it to. So for example, if I've got 10 to the third power and I take the log of that, the log of 10 to the third is simply equal to 3. And it's that easy to do. So you tell me, what's the log of 10 squared? Hopefully you immediately said 2, because it really is just that easy. The log of 10 to the 2 power is 2. And actually, there's even an easier way to think of it for some numbers. We can note that for 10 to the 1 power, that is 10. For 10 squared, or 10 to the power of 2, that's 100. For 10 to the power of 3, that's 1,000. The number that you get here is the number of zeros that you have. So notice this guy, 10 to the third, is got 3 zeros. 10 squared is 100. It's got 2 zeros. And so you can, if you're, instead of given the number like 10 to the third, if you're given a number like this, you can literally just count the number of zeros, and that will give you the log of that power of 10. Now, if you have negative exponents like 10 to the -1, remember 10 to the -1 simply means 1 over 10. The negative exponent means it's 1 over, and so that's going to give you that kind of a fraction, but that gives me 0.1. The log, so 10 to the -2 gives me 0.01. The log of 10 to the -3 gives me 0.001. And so you can kind of see a little rule of thumb here. If the exponent is negative, if I count the 0 before the decimal place, the number of zeros is again the number of my power. And when I take my logarithm, that's the number that I'll get. So here we see 3 zeros for 10 to the third, 2 zeros for 10 squared, 1 0 for 10 to the 1 power, which is just 10. Now, What is 10 to the 0? 10 to the 0 is actually 1. Anything raised to the power of 0 is 1. That's just a rule from mathematics. And so there's 0 zeros. And so you just have 10 to the 0 gives you 1. And it turns out, guess what? The log of 1 is 0. There's 0 zeros. The log of 0 zeros is 0. Now, let's do a quiz real quick. What's the log of 1,000? I hope you said 3, because the log of 10 to the third power is equal to 3. But we could have not even done that. We could simply count out that there are 3 zeros here, and so that's going to give me 3. Now, what's the log of 1? How many zeros are there? There are no zeros. So the log of 10 to the 0 becomes 0. Okay, so what is the log of 10 to the minus 7? I think you probably guessed it. It's going to be minus 7. It's that easy. So let's apply this again to our definition of pH, concentration. And so we know that the pH is going to be minus the logarithm of hydronium ions, the concentration of hydronium ions, moles per liter here. So for acidic water, the pH is less than 7. So for example, let's imagine we have 10 to the minus 5. If that's our concentration, 10 to the minus 5 moles per liter, we simply take the negative log of that. We get negative 5. Why? Because the log of 10 to the minus 5 is minus 5. Minus times minus makes plus, and our pH is 5. And so, again, here we have a basic pH scale, and we can see neutral gives us a pH of 7. The concentration is 10 to the minus 7. As our concentration gets bigger, that is, more hydronium ions, we become more acidic. And as our concentration gets less, that's fewer hydronium ions, we become more basic. And so you can see pure water, saliva, milk, rainwater, these are becoming more and more acidic all the way up to lemon juice, battery acid, and concentrated hydrochloric acid. On the basic side, you've got pure water and then blood, which is slightly alkaline, seawater, baking soda, etc. By the way, sometimes you hear people hawking diets that alkalize the body, that make your body more alkaline, and somehow that's supposed to make you more healthy. Don't believe it. It's a bunch of nonsense. Your blood is kept at a very slightly basic pH, and if your blood becomes a little bit more alkaline or a little bit more acidic than it's supposed to be, you die. And so your body is really, really good at keeping your pH in the range where it's supposed to be. So don't fall for the scams. And you know, I was amused by this meme that I saw about some celebrity that was selling alkalized water. That means water that's a little bit basic. And in the advertisement, they were spritzing it with lemon juice. If you take something that's a little bit basic and you add an acid to it, what happens? They neutralize one another. And so even if there was a particular benefit for having slightly alkalized water, and really there's not, but if there were, if you were putting lemon juice in it, you would kind of destroy that benefit. So it's a little bit silly. But anyway, just be aware of that.